So today we're going to do something that's a little bit atypical, which is to spend the whole class constructing a counterexample. Right? That's the goal of today. So right, the claim, right? So we're going to be constructing a counterexample to the claim that if f is continuous on the circle, then its Fourier series converges. Everywhere. Okay, so this is what you wish would happen, but in fact it doesn't happen. And in fact, one can construct things where one can, like I said last time, there's a whole industry at one point of constructing counterexamples which diverged on on large sets, like sets of you can, like sets that were dense, sets that are dense in the circle. Okay. And so the sort of like the critical example is to use the Fourier series of the sawtooth function. So use what they're calling the broken symmetry example for the sawtooth function. Okay. So the sawtooth function, I don't remember if I assigned it or not, but there's a function that looks like this. Right, looks like this on the circle, and then you extend it periodically, right? So it looks like looks like this, and then it has as its Fourier series summation e to the in theta over n, and from negative infinity to positive infinity, but nothing at zero. Okay. Right, times some constant. So, hey, Kai. Okay. So what we're going to do is take just the negative frequencies of the Fourier series for the sawtooth function. Okay. This is what they mean by taking a broken symmetry. So instead of taking the full symmetric, nicely symmetric Fourier series, we're going to look at this Fourier series. Only over the negative frequencies. Okay. And we're going to call that, say, okay. So the first thing we're going to see is that this cannot arise as the Fourier series of a Riemann integrable function. Okay, this cannot arise at the Fourier series of a Riemann integrable function. And the reason is, well, suppose it does. Suppose you have a Riemann integrable function that that has this thing as its Fourier series. Okay. Well, in that case, consider the Abel means. The Abel means of the partial sums of the Fourier series. Okay. Right. We're going to get right. In that case, a sub r f theta is going to be summation. R to the absolute value of n, 1 over n, e to the in theta for n from -1 to negative infinity. Right. Okay. Okay, so that would be its Abel means, right? For the partial sums of the Fourier series. Okay, but we know that that is expressible as the convolution of our function against the Poisson kernel. Okay, so so from that you say, well, look, this f is bounded, right? Since f is bounded by pi over 2, right? And the Poisson kernel is also bounded by 1. We get that that this thing is bounded. Right, you're taking a convolution of something bounded against some, against this kernel. Right. Sorry. The L1 norm of the Poisson kernel, because the L1 norm of the Poisson kernel is 1. When you convolve against it, then you get something bounded. Okay. Right? Is that okay? Do you guys get that?
Yes.
Yeah. Okay. Good. Okay. But if we look at AR f at 0, AR f at 0, right? Well, that's going to give negative summation r to the n over n as n goes from 1 to infinity. Right? Right? Take theta to be 0, this thing vanishes, and then I'm just going to rewrite this as using the positive indices. Okay. But as r goes to 1, from below, this goes to infinity. Okay, and so that's a contradiction. Right. Is everything okay? So right, we have our we have our Poisson integral, right? We have our Poisson integral, right? And this thing is controlled by the size of the thing, right? But this is bounded, right? This thing is bounded, so we can replace that with pi over 2, and then we just get the L1 norm of the Poisson kernel, which is 1, right? So this is bounded by pi over 2. Okay, so this is bound. This number should be bounded, right? For all it's bounded by pi over 2 for all r. But as r goes to infinity, we get infinity. As r goes to 1, then we get infinity. Okay, so this was the sort of crucial example. Okay, the crucial example. We've created a so what have we done? We've created an a Fourier series that cannot arise as the Fourier series of a Riemann integrable function. Okay. And that's what we're going to use this thing to create our counterexample for the claim. Okay, right. So the claim is, what you really hope will be true is that continuity implies convergence everywhere, but we're going to use this thing to construct something which is continuous, but whose Fourier series diverges. Yes.
But I was going to say, is this not because? Well, I thought that because the Fourier series doesn't converge, we can't hope for, let me organize this a little better. If the Fourier series does converge, do we know something stronger about it? Because I'm looking at this and thinking, it looks like 1 over n. So of course it can't be bounded at theta is 0.
Well, so we're not saying that this is the function,
Right.
Okay,
We're saying
what
that
we're saying
this is
this
the, yeah,
arises as the Fourier series
as the
of
coefficients.
functions.
Yeah.
Right. And so the question is, could this arise as the Fourier series as the coefficients of the function? And the answer is no. That's all we're saying. We're not saying
Okay.
we're not
I
saying more
understand.
than that.
Wait, you said could this arise as the coefficients of a function?
Could this arise as the Fourier coefficients of a Riemann integral function?
Right, and it can't be a Riemann integrable.
Right, it can't be a Riemann integral. Yeah.
Oh, I understand. Yep, gotcha.
Okay, so now we're gonna construct. Okay, so I hope everybody's. Anyway, what those of you coming in late, the moral is basically that taking half of the Fourier series is bad, or does bad things. Okay, and we'll take advantage of that badness to construct our counterexample. Okay, so here we go. Okay, so we're going to construct the bad series basically from the sawtooth function. Okay, so let's put up some notation here. So fn theta is going to be the sawtooth function's Fourier series. So up until a certain point. Okay, and then fn theta tilde is going to be the negative half of that. Okay, so and from -1 to -n. Okay, and the first thing to notice, we'll make two observations. The first is that fn tilde at 0, fn tilde at 0 is in size bigger than some constant times log of n. Okay, and that's straightforward, right? Because fn at 0 is just going to be it's just going to be 1 over n, and you're summing from 1 to n, right? So that's just the integral test or something like that, right? You've seen this in Calc 2 probably. Okay. Okay. The second thing is going to be much harder to show, and that is that fn theta, the non-broken, the one with the non-broken symmetry is actually uniformly bounded in n and theta. Okay. Okay. So right, the ones that have their symmetry are good. Okay. So to get the second one, we'll need to invoke sort of like a technical lemma. So roughly speaking, what we're doing now is sort of like the technical portion. Okay. Once we get these two things down, then we'll construct. Then I'll sort of outline the strategy to construct the counterexample. Okay. But first we're going to do some technical work. So lemma is the following, that right. So suppose you have an infinite series. So if the Abel means C sub n R to the n is bounded as r goes to 1. And 2, the coefficients are of order 1 over n as n goes to infinity. Then, in fact, then the partial sum sequence S sub n partial sum sequence of the C sub n's is bounded. Okay. Okay. So okay. So the proof is that we're simply going. So let me call these guys A sub r. So the strategy is simply to look at the difference between A sub r and S sub n, and we're going to control that. Okay, and you'll see that the decay of this size condition on the coefficients actually gives it to us pretty easily. Well, not easily. But
Is that
yeah.
big O or little O?
That's a big O. Okay, so what do we do? Right, we want to. These guys are bounded. We want to show these guys are bounded. So let's look at the difference, right? So consider, right, the size difference, Sn minus A sub r, right? So we have this minus this. So we're going to break the second sum into two parts. Right? The finite part and the infinite part. And then we'll combine these guys. We get C sub n 1 minus r minus this guy. And let me just put absolute values on everything. Right? We get that that this thing is less than or equal to this plus this. Okay. Okay. So now we're going to do something something very simple. We're going to do something very simple, which is we use the fact that, so recall that 1 minus r to the n can be written as 1 minus r times 1 plus r plus r to the n minus 1. Right? Standard trick. Right? And so, right, r is less than 1, and so this thing. Right. This thing in size is less than n, so we get a bound of n minus r. So what do we have right now? That this thing is smaller than summation n C sub n 1 minus r. N plus summation something plus 1 to infinity, right, C sub n r to the n. Okay. So right. So we're not doing anything. So here's where the 1 over n, big O of 1 over n comes in. Right, so C sub n is big O of 1 over n. Right, so we know that n times absolute value of C sub n is bounded by some constant at big N. Right, that's what this means. And further, that for n bigger than or equal to n plus 1, we have that C sub n is smaller than capital N over n. Right? Is that okay? Okay. Right? Because they're all the C sub n's are all smaller than m over n, And if n is bigger than n plus 1, then certainly we have this one. Right. So okay. So now let's put that together. Right. So we get so that term, that last term, is controlled by m times. So right. So what's the point? This one, right? This thing is controlled by m times n times 1 over r. Right. All these guys are smaller than m. Right. So we can pull that out. We get m times n times 1 over r. Right. And then these guys are smaller than. So we can pull out the m over n summation n plus 1 to infinity r to the n, right? But this thing is just part of the geometric series, so we get that this is smaller than this. Okay. At this point, we say let r be 1 minus 1 over m, capital M. Okay. So that may seem like some sort of trick, but what you do, the reason you do that is because you say you look at this expression and you say, where is this thing smallest? For what r is this smallest? So you go back to calculus and say minimize this expression for r. Okay, and then it turns out that when r is 1 minus 1 over n, you get the smallest number. Okay, so that's where this comes from. Okay, and so you substitute that in, right? And this turns into 2n. Right. 1 minus 1 over n gives you 1 over n. That cancels out here, right? And then it works out here also. So you get 2n. Okay, so right. So what have we shown? We've shown that that the distance between these guys is controlled by 2m, right? And since the ARs as r goes to 1, the ARs become bounded. We know that the ARs are bounded as r goes to 1, and so that tells us that the SNs are bounded. So. Okay, so that's the technical lemma, right? That if the Abel means of an infinite series is bounded, and the coefficients are big O of 1 over n, then the partial sum sequence of the infinite series is bounded. Okay, so now we're going to use that to get the fact that we wanted, right? We remember we wanted that second fact that the sorry, just
uniformly bound.
Thank you. Yeah, that the partial sums of the Fourier series for the sawtooth function is uniformly bounded in n. Okay, so maybe I'll leave this up. I'm going to erase. I think I can probably do it. I could probably do it over here. So let's do that. Okay. So now we want to show that fn theta EPN theta over n, that this thing is uniformly bounded. Okay, and so we're going to use we're going to use this. We're going to use the lemma. Okay. So so what do? We say let C sub n be e to the I n theta over n plus e to the negative I n theta over negative n. Okay. So this is going to be the infinite sum that we care about. Okay. And you can see that the C sub n's are of order 1 over n, obviously. Okay. 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 So now, if we consider S of n, the partial sums, right? The partial sums of these guys is just from n from 1 to capital N, e to the I n theta over n plus e to the negative I n theta over n. Right? But that is, of course, Fn theta. Right? That's Fn theta. Okay. So, okay. So, right. So now let's look at the Abel means, right? Yeah. Okay. So now let's look at the Abel means, right? The Abel means is this thing here, r to the n e to the I n theta over n plus e to the negative I n theta over n. Right, that's the Abel means of our series, right? That's the Abel means of our series, but that's also the Abel means of the partial sum of the Fourier series for the sawtooth function. Right? So this is also this, right? Where f is the sawtooth function. Right. Okay. Now that's bounded, right? Well, as we mentioned before, that's just the Poisson. That's just this convolved against the Poisson kernel. That's bounded, right? So what does that tell us? That tells us that our Abel means are bounded, right? And so the conditions of the lemma are fulfilled, right? Remember, we needed the Abel means to be bounded. We needed the coefficients to be of order of big O 1 over n, right? So say, well, look, the Abel means of our series are actually the Abel means of the Fourier series of the partial sum of the Fourier series of the sawtooth function, right? Which we know is bounded, and so this gives us bounded, and so we get that everything is bounded, right? So these guys are bounded, and the point is that that this, right? This is bounded, independent of theta, right? So this is bounded independent of theta as well, right? So you might, in case you're worried, right? You think, oh, we've only got it in terms of n, but theta, this thing is bounded independent of theta, so that gives us the theta as well. So. Does it make sense? So basically, the trick, if it can be called a trick, is to transfer from the Abel means of the series to the Abel means of the function. Okay, let's go on. There's only like 18 minutes. Shoot. Okay, so now we're going to construct the counterexample. So this is actually really fun. So I hope you like this. Okay, so again, right, so again, we've got our S of n, which is the sum of these guys, and we've got our Fn tilde, which is just the negative guys. So, right. So the way you want to think of these guys is that they, these are constructed from the sawtooth function, right? So this is like you're chopping off the sawtooth function at various from from negative n frequency to positive n frequency. So you're chopping it. You're sort of like a band. You've created a band limited version of the sawtooth function, right? Right. And then this is just the negative frequencies of that guy. So as n gets bigger and bigger, you're basically creating a more and more precise copy of the sawtooth function. Okay. Okay. So we take each of those guys, and then we're going to shift them. I think call it like these guys are like trigonometric polynomials of degree n. Right. They're both considered trigonometric polynomials of degree n. Okay. So now what we do is we're going to create a new function by taking copies of these guys and sticking them at various frequencies. Okay. So you like take copies of the first guy and you stick it at a particular place. You take a copy of the second guy and you stick it at a particular range of frequencies. Right? Each of them has a limited range of frequencies. So you just say, I'm going to shift you to this range of frequencies. I'm going to put the second guy over here. I'm going to put the third guy way over here so that they don't interfere with each other. Okay. Okay, and that's basically going to be our bad function. Okay. So so we need some notation, which is the frequency shift, which is so we notate p sub n theta as f sub n theta, but shifted by e to the I 2n theta. Okay, so we've shifted all the frequencies by 2n, right? So now this guy whose frequencies were between negative n and n, the frequencies are now between between n and 3n, right? So now this guy is of degree 3n, right? So its frequencies were between negative n and n, and we've shifted them by 2n, right? So they now go to n and 3n. The frequencies are now here. Okay. Similarly, we do the same thing for the twiddle guy, the broken symmetry guy. Okay, so that guy's frequencies were between negative 1 and I'm sorry, negative n and negative n and negative 1, and now they go to this is a degree 2n minus 1. Okay. Right. The frequencies go from n to 2n minus 1. Okay. Okay. And now we make some yeah. Okay. So so again, sort of like a technical observation. If we take the partial sums of the p sub n, right? Then if m is bigger than 3n, then of course we're just going to get p sub n back, right? Because this says, what does this guy say? It says chop off the frequencies at m, right? At the mth degree, but the degree of this is 3 sub n. So as long as we are bigger than that, we're gonna recover the whole guy, right? If we chop off smaller than n, right? If we say we're only going to consider the frequencies between here and here, well, we get 0, right? Because it has no frequencies between there and there, right? And if we chop off at 2n, right? If we chop off at this point, well, we only capture the lower frequencies, right? In other words, we get p sub n tilde, right? Because the partial sum operator just says chop off the frequencies between negative n and positive n, right? So this is, I hope this is completely obvious. Okay. So so now we're going to do the construction. We say so we choose okay. So what we're going to do is we're going to define f as a linear combination of various copies of the shifted guys. Okay. So this is what I was saying earlier, right? Each of these, as k gets larger and larger, each of these becomes a more accurate or more precise copy of the sawtooth function. Okay. But we're shifting them down the line. Okay, so that they don't lie on top of each other. Okay, so we've got like we'll take part of the sawtooth function and we'll shift it down the line to a certain range, and we'll take a bigger copy of the sawtooth function's frequencies, and then shift that farther down so that they don't interfere with each other. Okay, and then what's going to happen is we'll look at the partial sum operators. Right? The partial sum operators are going to be bad if we chop them in the middle, right? So we're going to chop each one in the middle. We're going to chop each one in the middle. That will give us the bad part of the sawtooth function, right? Which at 0 is going to increase like log of whatever it is.
Log of big.
Yeah, log of big N. Yeah, log of big N, right? So as you go onwards, the behavior at the origin is going to get worse and worse, right? And that's what causes the divergence at 0. Okay, but you have to sort of finesse things so that one, that this converges, and two, everything sort of works out nicely. So there's a little bit of finesse involved, but it's actually not that resistant, right? Like this counterexample. Like this is not too bad for a counterexample. Yeah. This is fine. Okay. So yeah. So what do we do? 10 minutes. Okay. So so the question is, of course, what are we going to choose? Right, we have to choose our coefficients, and we have to choose our coefficients, and we have to choose our shifts and frequency ranges, right? So that things work out. Okay. So here's the thing: choose any positive convergence series, summation alpha sub k. And n sub k, sequence n sub k, such that when the n sub k's are always bigger than 3 times the previous guy. Okay, this is that business of trying to stay away from the previous guys. You don't want avoiding the overlap, right? That's what's going on here. And 2, you want the limit of a sub k log n sub k to go to infinity, right? This is what causes the divergence. Okay, right, and they give an example for possible numbers for these. Okay, and then so maybe I should write like this. Let this be that where we've chosen any positive convergence series blah, and this such that this happens. Okay. Okay, so now, here, to remark that p sub n of theta in size, right, is the same thing as f of n theta in size, right? Because this thing, shifting it doesn't change the size. Shifting the frequency doesn't change the size, right? And this was uniformly bounded, which was uniformly bounded. Right, these guys are uniformly bounded, and so since the series converges, we have that this thing converges uniformly. Right, so f is a continuous function. On the circle. Right, by Weierstrass. By m-test. It's okay? Okay. Okay, so now here's the key claim that for all m greater than 0, if we take this particular partial sum to n sub m f and evaluate it at 0, then we get this sort of bound. Okay, it's going to be bigger than a sub m times the log of n sub m plus some sort of constant, something on the order of constants. Okay. Okay. So let me do that over here. So let's do that, right? S2 sub n m f evaluating 0. Okay. So we shift the partial sum operator inside. Oops. Okay. And now we say, well, let's break this up. Break this up into our three parts, right? So we break it up into 3 parts. One where m is less than k, one where m equals k, and one where m is greater than k. Okay. Right. If we take the partial sums where m is less than k, well, because that would mean that we're less than a third of the lower range of the frequencies for this guy, right? By this, right? And so we're not gonna get any of this. We're not gonna hit this guy's frequencies, and so we get 0. Right? This is 0. Right. When m equals k, well, we get the broken symmetry thing, right? Because now we're chopping it right in the middle of its frequencies. So we're only going to get the left half of it. So we get the shifted broken frequency guy, right? And then for the right, and so we end up with summation a sub k. For this, we actually do get something, right? These things actually do persist, right? We get something. So, okay. But when we look at that thing, okay, zero, right? Right, what's the point? The point is that, right, so let's look at this last term here, right? If you look at the last term, let's look at the size of it. Well, that's controlled by, you know, a sub k, p n k, 0, right? Controlled by that. The alphas were positive, right? But again, this is the size of, the same size as f sub nk, right? Because this was just the shift in them, right? Just a frequency shift. And these were bounded. This is bounded by some constant. Right? And so we get this thing is bounded by, you know, that constant times whatever the, you know, this was a convergence series, so it converges to bounded by some alpha, some a, right? And so that's it, right? We get, you know, this thing has the right, the shifted, you know, the broken frequency guy at 0, remember it was of size log of nk, right? So p and m tilde, if we evaluate it at 0, we just get f and m tilde, right? Because this guy was that guy times e to the I2 nm theta, right? But for theta equals 0, that just vanishes, right? And so we get this, but we know that this was bigger than constant times log nm, and so we get our constant. You know, we get our logarithmic growth. We get this constant that's uniform, and so, you know, as m goes to infinity, each of these s sub 2m's will head off towards infinity also. Okay, so we get a sequence of partial sum operators that behave badly as we go to infinity. So we have that, you know, that we have divergence, right? So the Sm, the partial sums diverge at 0. Pretty cool, right? I hope you liked it, right? It's fun, right? You take copies of the, like, increasingly accurate copies of the sawtooth function, you shift them over to like distance spaces so that they don't interfere with each other, and then you notice that, you know, because of the broken symmetry, if we take the right partial sum operators, we're going to hit it exactly at the bad place. Right? We get at the bad place, and then there's head off.